Hey there, I'm Nix, and the topic of today's video is tackling the third maximum number problem on the LeetCode website. As always, solving this problem in the C++ language and giving you a detailed explanation of the entire process through the planning of the algorithm to the coding of it to the analysis of the time and space complexity as well as looking at the LeetCode rankings. If that sounds good to you, then stay tuned. Welcome back. Now again, before we get started, last time I solved the height checker problem, and now we're on to third maximum. And as you can see, we kind of had a forcible skip over to this problem because the max consecutive ones to problem is premium access only, and I don't have premium. I'm only solving the free problems that you have access to without having to pay money. So, no premium access, no premium problems for us. So, that's why we're on to this problem. Moving on, let's start tackling third maximum number. So we're given an array that we're calling nums, and we want to return the third maximum number in this array. If the third maximum does not exist, however, we want to return the maximum number. Now, going through the examples here, you drive that point home, a 3, 2, 1 array. Since we have three numbers here, one is the third maximum, with 3 being the max. So we output the value of 1. In this array that isn't long enough for a third maximum to be possible, since it only contains 2 numbers, we report the maximum value instead. But this example here is a really useful one, because we have 4 numbers, we have 3 distinct ones, and we output 1 instead of, say, 2 because it's the third distinct value. And that's a good clarification to have. Looking at the constraints, this is also going to give some very useful information. Never given an empty array, but the thing to really notice is that the values that the integers can take on span the entire range of what an integer value can hold, from -2 to the 31st power to 2 to the 31st minus 1. And this follow-up one asks us if we can find a big O of n solution, which, yes, we're going to go over about 3 different ways to approach this problem. The first of which is only going to take a few lines of code, and it's going to essentially have a new container that we create do some of the hard work for us. And the container that I am thinking of is a set. Using a set container is very useful for this problem because sets only allow unique values present in them, and they are automatically ordered. So if we have any duplicates present in an example, it's going to not even allow them into the set, and it's going to auto-order them. So once we've created the set, we know at the end of the set is where our maximum number is going to be, and 2 places away from that is going to be where our third maximum is. So we build a set, we go through our initial array and add stuff to the set, and then we determine whether we're going to report the maximum number or the third maximum depending on conditions. With the condition being, if our set's size is less than 3, we automatically know we don't have a third maximum and we should report the maximum. If it is bigger than 3, we know we have at least 3 distinct values, so we are going to report the third maximum in that case. Depending on what we return is dictated by the size of our set. And that's pretty much all of the core parts of this algorithm. So let's move on to coding that first solution. Okay, variables first. So we create a set of integers, and I've just named it ordered numbers. Next up is filling up the set with the numbers from nums. So use a ranged for integer number in nums, and for every value that I call number in the nums array, we're going to call ordered nums and the insert function and just plonk the number value in there. The final thing to do is to return our maximum or our third maximum depending on how big our set's size is. So if our size is less than 3, we know we don't have a third maximum present. So we want to return the maximum value. Now, how do you get the maximum value in that set? Well, you can use the iterator here, reverse begin, which essentially points to that last position within the set. And I'm just using this in array form as an example to make things easier and present it in a way that's easy to type. So reverse begin points to the last thing in the set, the end of it. But this is essentially a pointer. It's referencing a position in memory, an address. That's not the actual value. We want the value, not the address that it's looking at in memory. So in order to get that information, we essentially need to dereference a pointer, which is what this asterisk does. Dereferencing a pointer gives you the value in that position instead of the position itself. Similarly, if the size is 3 or greater, we know we have 3 distinct values at least, so we have a third maximum that exists. Now, how do we get to that position? Well, in this case, I used the end iterator, and the end iterator doesn't actually point to the end item in whatever container you're using. It points to the position that is outside of that container. So in order to get to the third maximum here, we can use the next function. And the next function moves the iterator that you're using over how many places you tell it to go. In this case, we're going to shift it -3 positions. So shifting it left, we're essentially shifting it in reverse. So in this case, in order to get here, which is our third maximum, from here beyond the end of the array, we need to shift it over 1, 2, 3 places total. If you use the reverse begin iterator here, then you would only need to shift it 2 places because you would start here, still want to go here. So this code is finished. It should work. So let's verify that before I do anything else. Pending finished, 1 equals 1. This is good. Let's submit for the full shebang. Pending, judging, and green text. Yes! Always good to see. Okay, again, before we press the button, let's go over time and space complexity for this. Now this is very easy code to write because, again, as I said, we're essentially letting set do the hard work for us. It's removing all of the duplicates and it's automatically ordering stuff. So the only thing we had to figure out is how to reference the relevant positions in the set in order to get the values that we're interested in and return those. But in creating this set, we are taking extra space in memory that is dictated not so much by the amount of numbers in nums total, but by the amount of distinct numbers in nums. So the size is going to be equal to, let's say, n, where n is equal to the number of distinct values in the original array. Now you can add extra code to optimize this and essentially only get to a point where the set is a size of, say, 3, but that requires additional code, and if you do want to optimize space, there are better ways to do it that also optimizes time. So I'll leave that for you and for a future video to address, in addition to in an effort to not make this video too long. Anyway, in terms of time complexity, we have a for loop here, but be careful. You're also within that for loop using an insert function. And set operations have a time complexity attached to them of log n, where n is equal to the size of the set. But here in the for loop, we're dictated by how many numbers total are present in the nums array. So in this case, our time complexity is going to be a multiple of the time complexity of the for loop multiplied by the time complexity of this insert function. Now the for loop we can say is dictated by a different variable. Since we're using n to equate to the number of items in the set, let's say the number of items in the original array is equal to m, not n. So this total time complexity would be equal to m log n. So not the greatest in terms of space usage, and not the greatest in terms of time usage. Ideally, we'd want to find solutions where we just take constant space usage, big O of 1, and create a big O of n solution, which will be for the future. But first, let's take a look at rankings. Okay, very small distribution, and we can have improvements that are possible. So not surprising that we're low on the range here. And we have our memory usage being at the very bottom here, which makes sense because this use of the set function takes up some space in memory, especially with the way it was implemented, where every unique value in the original array is being plunked into the set. So definite improvements to make. Okay, this was a set solution using that container, but let's now take the load off of that set and do the hard work ourselves. So let's think through how to find this third maximum number. Well, we can have a couple of variables, maximum, second maximum, and third maximum. And those can be used to house our relevant values. And we know we're going to need to go through the array and update those values depending on the value that we see. Now, if we come across a value, and let's take an example here on my whiteboard. Let's say we're trekking across this array, and when we get to the 3 position, let's say we have our maximum, our second, and our third housing those 3 relevant values. Max is 3, second is 2, third is 1. But what do we do when we come across 5? Well, 5 is bigger than our maximum that we currently have. But if we just immediately replace that value with 5, then our second maximum and our third maximum are now wrong, because the second should now be equal to 3, and our third should now be equal to 2, with our old third dropping by the wayside. So if we're looking at various numbers and figuring out which value to replace, if we're replacing that value directly, we need to first cascade down the values beforehand before we update our number. So in other words, we need to make sure that we assign the third maximum to what the second maximum was, the second maximum to the old maximum, and then we can assign the maximum value to that new number that we see. Now the same thing happens if we find a number that is, say, less than the maximum, but higher than our current second maximum. In that case, before we replace second maximum with the new value, we will first have to still cascade down those values so that the third value equals the second value, and the second value then gets updated afterward with the new value. And for every single bin, we need to make sure that happens. Now, we also need to make sure that we're dealing with duplicates. And the very first thing that we check for is those duplicates. And if it is a duplicate, in other words, it's equal to the maximum already, it's equal to the second maximum, or it's equal to or lower in value than what our third maximum already is, then we can just skip over that and continue with our additional checks. And that's a perfect way to use the continue keyword in C++. So we have a way to handle duplicates. We know to cascade down depending on the situation and the number we see. But there's one last thing we have to address. what do we initially assign our maximum, second, and third values? Ideally, we could assign them a value that is never going to show up in the actual array. It's lower than any possible value that we could see. So if by the end of going through the array, our, say, third maximum still equals that impossible value, we know that the third maximum doesn't exist in the array, and we can return our maximum instead. If it doesn't equal that number anymore, well, it got replaced during the for loop, so it exists, so we return it. But this constraint comes into play. This constraint means that it's the full range of the integer value. So if we want to go and house a value in our variables that's lower than any potential value we could see, we can't have our variables be an integer. So the way to get around that is to assign them a variable type of long, because a long has a bigger capacity and can house bigger numbers than an integer. So using that variable type, we'll get around being impaired by this range. With that being said, that gives us a pretty good roadmap for coding out our second solution to this problem. So let's get down to the code. So here are the 3 variables to use, and again, they are of type long. We have max number, we have second max, and we have third max, and all of them are equal to a value that is lower than any potential thing we could possibly see in the array. Any value that is lower than -2 to the 31st power, which turns out to be -2 billion and some change, will work. And the first thing that popped into my mind is -3 billion. So that's what I assigned all the numbers to. Okay, next up is the for loop. And again, it's arranged for. So for every value number in the nums array, we're going to do stuff. The very first thing to do is we need to skip over those duplicates and values that are less than what our third max is already assigned to, since those numbers are not relevant. So if the value that we're looking at, number, is less than or equal to what our third max is already assigned to, then we skip over that by the continue keyword. We also want to do that if we have a number that's equal to the second maximum, or we have a number that's equal to the maximum number already. All of those would be duplicates or values less than the third, which we don't care about. So all of those are skipped by using continue. This if statement is going to handle our first cascade. So in the situation here, we have a number that is greater than our maximum. So we set our third max to what the second maximum equals. We set second maximum to what the maximum number currently is, and then we update the maximum number with that new higher value that we've seen. The next thing to check is the scenario where the number is less than the current maximum, but it is also higher than that second maximum. So we need to update the second max and the third max as a result, but our maximum number is still good the way it is. So again, third max equals second max, and now second max we can update properly with the new value. The final situation we deal with is if we have a number that is less than the second maximum, and that number is also higher than our current third maximum. In this case, nice and easy, we just set third maximum equal to that number, and no cascade is necessary. Finally is our return statement, and this is using a ternary conditional statement. This thing is going to return one of 2 possible things depending on whether this condition is true, using the conditional operator here. So this reads, you want to return something if the third maximum equals that impossible value still, then you return max number. If this is not true, return third max. With all of this code, everything should work. So let's prove that. Pending judging 1 to 1, that's good. Let's submit here. Pending judging and green text. Lovely. Okay, Let's go through time and space complexity analysis. The only thing we are creating are some long variables. Those are constant space usage, so we have achieved big O of 1 space complexity. Woohoo! For our time complexity here, we are going through the nums array. So let's say that variable is equal to n. And within the for loop, we're essentially doing nothing but if statements and simple assignments, which is all constant time usage work. So this entire for loop is just going to depend on the number of things in the num array. So this for loop is going to have big O of n time complexity, which means we've fulfilled the follow-up condition. Big O of n time complexity, big O of 1 space complexity. Excellent. So we should be higher on the rankings as a result. Okay, cool. We got bumped up into this bracket here. Excellent. And in terms of our memory usage, we've vastly improved, and we're now into this distribution up here, as we expected. Excellent. Now, let's do some tweaks to this second solution and see how we can solve it in a different way. Now, in this solution, we were looking at the value, and we were making an assignment depending on what condition that number fulfilled. So we were doing a proper assignment and then cascading down our assignments to make it fit where it's supposed to be. However, instead of cascading down, what if we promote up? Assuming we're dealing with the duplicates in the same way, what if we automatically assign a value to the third maximum and then switch numbers depending on whether now that third maximum is higher than second maximum, and if second maximum is bigger than maximum, well, we switch those numbers. So instead of cascading down, we promote up. So let's see how this code would change if we do that. The first change I did is instead of having 3 billion. Basically, if you can't quite remember those benchmark values, the minimum and the maximum value various things can hold, then there's an easy macro that is automatically assigned to those values. And setting a variable equal to it is a nice easy way to avoid having to memorize them, especially if you need to use that exact value. So any value would work, as you saw. Assigning it randomly to negative 3 billion does work. But to make it a little neater, you can use L long minimum, and that automatically assigns this variable to the minimum possible value that long longs can take on. The next thing I want to add is this value here, temp holder. This is going to be used for switching around the values. Now note, I can use an integer value here as long as I'm careful about my assignments for this variable. We still want to check for duplicates and values lower than the third max, so this branch can stay, but let's get rid of all of these branches here in order to do our promote up approach. First thing to do is automatically assign the number that we're seeing to third maximum, because if we pass through this if check, we know that that number has to be greater than third maximum, at least in the scenario. This if branch here is going to check, now that we've made this assignment, is that third maximum value greater than our second maximum value? If so, we need to switch things around. And we need to do it in a way that, because this is an integer value, it never has the possibility of holding a long value. Because if it does, we're going to have overflow problems and mess things up. So the first thing to do in the swap here is to assign temp holder to that third maximum number, because after this line, we know definitively that third maximum cannot possibly be a long value because it is housing something that was present in the nums array. And in this scenario, let's say we're going through the array and we find 3. So after this line executes, our third value is now 3. But maximum and second maximum are still that super duper negative value here. So we compare the second maximum, which is that really large negative value, and third maximum, which is 3. 3 is definitely bigger than a very large negative value, so we need to swap these. So we assign a temp holder to that value, 3. Now we can replace third maximum with second maximum. So this negative value is now housed in the third maximum. And now we can overwrite second maximum with the value that our temporary holder has here. Now here we still have an issue. We have 3 in the second place and a deeply negative value in max. So after performing this check, we also need to perform another check to see if we need to switch second maximum and maximum around as well, which can be done by this statement. So in this if statement, we have if second max is bigger than what our maximum is supposed to be, we do a switcheroo again. And again, we want to make sure to assign temp holder to house what second maximum has, because by this point in the code, we absolutely know definitively that second maximum cannot possibly house that long value. So temp holder equals second max, which in this case, I don't have to do anything else because it already has it. And now second maximum equals maximum number. So the negative value here gets transferred back over to here. Now maximum number is going to house what temporary holder has, 3, and now you see that the 3 has migrated and been promoted up to where it is supposed to be. And no matter what array you're given, no matter what specific properties and sequences the numbers are in, this approach should always put the value assigned into its proper place. Again, the return value is the same thing here. Again, updating and using this little macro here. So those two if statements replace the old if statements, and this approach should also be able to handle anything that's thrown at it. So let's prove that. Pending judging finished, 1 to 1. Submit for the full shebang. No red text. Yay! No red text. Accepted. Excellent. And again, we have the same general time and space complexities. Objectively, with the way we performed the switch, we have a little bit higher memory usage because we had an extra temporary holder in creating this integer value. So we're using a little bit more space, but it's still constant space. So it's still on the order of big O of 1 space complexity. In terms of time complexity, still have just one for loop. We're still making constant assignments and doing if statements within it. Everything that we're doing is constant time work. So we're still at a big O of n time complexity. And we should be able to see that in the rankings. Yep, still here. And we are still in this distribution here. And again, take LeetCode rankings with a grain of salt because you can ping pong around a bit depending on backend things, server traffic. I don't know, you ping pong. So that was the third maximum number with 3 different ways to approach the solution. I hope you got something out of this video, and as always, I wish you happy coding and to have a nice day.